Great. So, hi everyone, I'm David, and we already had great introductions about eROSITA in general and why we want to do spectral analysis by Andrea and Sophie. And we already know how to extract spectra. So what I will be providing you with now is a detailed code of how to then actually analyze the spectra. And this code is not just for eROSITA spectra. It has to slightly be changed for other instruments, but mostly it's the same for all of them as soon as you have the spectral files. So first of all, a quick motivation why we want to do spectral analysis and particularly Bayesian analysis with X-ray data. So as Sophie already mentioned, we have individual photons, so we're counting photons, which means Bayesian analysis is the natural way of handling this data, this Poisson count data. Sorry. And what's also great about Bayesian analysis is that it's robust against low counts. We do sometimes have those very bright objects that Sophie and Pietro showed, but a lot of the objects look more like we have spectra like you can see on the right here. So in this plot, you can see the source and the background spectra. The source spectrum is the one with the normal crosses, and then the background is with the additional crosses in the center. And you can see that already here above 0.9 kV or 1 kV, the background starts to completely dominate, and also below, the background is quite relevant when compared to the source spectrum. And in order to then properly model this, we want to, for one, do Poisson statistic, and also want to model the source and the background together. An additional great thing about Bayesian statistic is that it's kinda harder to do overfitting with it. And our overall goal is to identify a physical explanation of our sources, which is why we want to do in-depth spectral analysis, or as good as we can, and to use this to guide our to guide our interpretation of the source that we're looking at. All right. So the way that we do this analysis, so the way that I'm explaining it is I'm using BXA and I'm using the XSpec implementation of it. As Pietro mentioned, one can also use Sherpa instead of XSpec. I'm just used to XSpec also because I'm used to the command line tools of XSpec. Right. So this is all the model, packages that we want to import. Then next, what we do is to do the XSpec initial setup. So there's some parameters in XSpec that we want to set in order to then have the models interpreted the way that we want them to be. The first one that already was mentioned by Pietro and Sophie is that we want to use the cache statistics, so the CStat. I'll explain on the next slide what exactly this is and why we want to use it. Then we can also set the abundances, so the elemental abundances, which will then be used for the absorptions. Then we also want to set the cross-section, and we can also set the cosmology. Right, so just a quick overview of what cache statistic is. Cache statistic is kind of similar to, or is similar to chi-square statistic, with the difference that it does not assume Gaussian distributed data, but instead it assumes Poisson statistics. So it's used for Poisson counts. And we use it because it's robust. So for one, because we have counts, and also because it's robust against low and zero count bins. And then the log likelihood is defined like this. So what we have here is it depends on the model prediction in a given bin I with a given set of parameters theta, and it depends on the counts. Right. So as soon as we have set all of those expect parameters, we start with loading our data. As the very first thing, what's typically good to have in your script is to first clear all the data and all the models in order to not have any remnants in there which can then influence your fits. Next, we then actually load the data. So in this case, actually one thing that I forgot to mention, this script together with the files that I'm using, I will also be providing you with a zip file so you can then look at the Jupyter notebook, because I think that's most practical. So you can actually see what happens there and test it yourself. Right. So, and we use this spectral file, which was extracted the way that Pietro showed us, and we load it into XSpec, which is done in this line here. The next, we do the same thing that Pietro already did, that we ignore data that's below 0.2 kV and above 2.0 kV. If you remember the spectrum, above 1 or 2 kV, that basically was nothing other than background. So by ignoring everything above, we minimize our background contribution. So we maximize our signal to noise ratio. Right. So this is then, this is again the spectrum. So you see above here, so here's the 2 kV. There's basically no source counts anymore, and most of it lies here. In the next step, what we do is to define our model. So what's great about XSpec is that we do not have to define the energy dependence or anything ourselves, but what instead we do is basically we use blocks that are already programmed and put them together. So in this case, what we do is we use an absorption and a power law component. So the absorption acts on the power law, and this is then our combined model. And in the next step, what's important for BXA, for all the parameters that we want to model, we need to set them quite precisely. So typically in XSpec, it's sufficient to just set the initial value. But then if we want to use BXA, we also need the boundaries that are set here. So the way that the setting of parameters in XSpec works is that you set the value, then basically like at which grid size it should be tested, more or less. Then you set a hard and a soft lower bound and a soft and a hard upper bound. I'll explain on the next slide quickly what those two are. So the bounds in XSpec are such that they're soft bounds, which are used for the fitting inside of XSpec. So during fitting, the parameters won't go outside of the soft bounds. And then additionally, there's the hard bounds. This is especially interesting to have them larger than the soft bounds if, for example, you want to be able to also set the normalization to 0. For example, if you want to be able to calculate the flux of only one single component, and then you set all the other normalizations to 0. What currently is an issue with BXA is that it is using the hard bounds for the priors. So if you want to have your priors set only on a specific range, you will have to set the hard bounds to this range, but this will be changed. Right. So we do this for all the parameters that we're interested in. So in this case, it's the absorption for the absorption component here. And then for the power law, we have the photon index and the normalization. So what you can see, the absorption is from 10. So in expect, the absorption works like this, that those values are multiplied by 10 to the 22. So the absorption is between 10 to the 17 and 10 to the 23. Right. And then the power law index is between 0 and 4, and the normalization is between 10 to the minus 5 and 5 times 10 to the minus 1. Good. So now we have set all our parameters, and with those ranges, we can next set, one more thing. I want to also show to you how model comparison works, and for this purpose, we define a second model, in this case, an absorbed blackbody. So the only thing that we change here is this here. And then, of course, we set different parameters. And then as soon as we did this, we can load the model and set the priors. So the way that this works in BXA is there's already predefined functions for which you just have to write what kind of prior you want to choose. So log uniform, uniform, Gaussian, then which model it should work on and which parameter it should be for. So in this case, it's a prior for an H. If you remember, it was over several orders of magnitude, so we definitely want to have a log uniform prior. And it's for model 1, so for the absorbed power law. And then we do the same for all the other things. So for the photon index, we want to have a uniform prior because it only varies within a relatively small range. And the normalization, again, is a large range, so we use a log uniform prior. Then what we need to do is to define a solver, which basically tells BXA which parameters or which priors it should use, and also where to put all the results. And as soon as we have this, we can run the fit and get the results. Right. And if we do this now for the absorbed power law and for the absorbed blackbody, we get those two results. And as you can see, the absorbed power law has problems here. So it definitely does not match that well already by eye. But now we want to actually compare the two models to one another. And the way that we do this is by using the Bayesian evidence. So a thing that most likely everybody of you is familiar with is the likelihood. But likelihood only gives us the probability of the observed data given specific model parameters for one specific model. So we can only compare different sets of parameters using the same model. But what we now instead want to do is comparing different models. And the way that we do this is by using the Bayesian evidence, which is basically the likelihood averaged over the entire prior space. This Bayesian evidence does penalize model complexity and large priors. So what this means in praxis is if a model is more complex but does not fit any better to the data, the Bayesian evidence will be worse than for the simpler model. And in addition, we also want to have priors as sensible as possible. So we don't want to just set it around the best fit value because we don't have any prior knowledge before fitting. But at the same time, we don't want to have it unphysically large. Right, and then using this Bayesian evidence, we can then compare different models, which in BXA is done with a script that I will be providing you, but that's also on the GitHub of BXA. And then this prints the base factors, so the basically the difference between the log evidences of the two models, and also it compares the likelihoods. This comparison of the likelihoods is interesting in the case of having minor adjustments in the model. For example, having a small Gaussian absorption or emission line added to an existing model, but not in this case where we're comparing very different models. So here the base factor is the important thing. But one can also directly access the parameters by those two lines. So we can directly go to the log C of the individual models, or solvers in this case, and also the log likelihood. Right. So now we have a fundamental understanding of how to fit a model, but what Shofir already teasered and what's also important is to actually fit a sensible model to the background, because then we can also model the source a lot better, especially for fainter objects. It's of course not physical to just subtract rates from one another, because the counts coming in is just given with a probability. So what we have to do is to actually model this probability. And modeling the background then becomes especially relevant if the background fraction is large, as you can see in this example here. The way that we have to prepare this is that we use a script that's also on the BXA webpage, and a file that exists for pretty much all large X-ray instruments. So there's specific files that give an information on typical background spectra that are observed with the instrument. Right. In case of eROSITA, this file is called eROSITA merged 1024. And we need to have this file in the directory that we run it, and then we run fit background onto the background spectrum that we got from the source extraction. So in the terminal we just run, oh, I forgot something. It should be python fit background.py and then the name of the spectrum. And what we get from this is then a table model, which can be used in XSpec or also in Sherpa, I assume, where we basically get a shape of the background, which can then still be scaled by a normalization. And then in order to fit for this normalization, in addition to the source spectrum, what we need to do is to add this spectrum when fitting with BXA. One important thing is that this background spectrum is not some kind of a physical spectrum, like it's not adding up all the different X-ray components that we would expect, but instead it's an unphysical combination of different functions that were found, which is also why it's not done in the energy space, but instead in the channel space, because it's not necessary to convert it to energies. Right, the way that we do this is to first load the data as we did before. So we again load the spectrum. In this case, we save the, we create an object of this spectrum. We call it source. And again, we ignore below 0.2 and above 2.0. And now comes the part where it diverges. The important thing is, because we have this additional spectrum that we want to fit, we need to have an additional response for it, because we're not working in energies, but instead in channels. And the way that we do it is, as you can see here, so we save the responses first, then create an additional response, and then later on we create a diagonal matrix for the response that we use for this table model. Right, but what we also do, one thing that I also forgot, in order to then also model the background, is that we set the background in the source region to none. So we don't do any background subtraction anymore. And then the next thing that is done is that we load the background spectrum as an additional data set. So the way that it is done in XSpec is that we here give the number of the data set and the group and load the background spectrum as an additional file. And then we again do the same thing with the responses as we did before. And now we create those dummy responses that we need in order to use this table model. We do need some additional information on the channel numbers that appear in the spectrum, and we can read this from the this JSON file. Yeah, those are just numbers that go into the dummy response here. So this here is for eROSITA, just the part that you need to copy paste. Don't need to think about it. For other instruments, this needs to be changed. Right. Then next, we again define our source model. So this is exactly the same way that we did it before. The only difference is that we don't immediately define the solver, but we save the transformations, so the priors in this list here, because we need to add one additional one, which will be the normalization for the background spectrum. And the next what we do is to load an additional model, which is exactly this file that we created with the fit background. And we load it as a table model and multiply it by a constant. Now, in order to one thing about the source and the background is that the counts are not directly related to one another, because typically the background region is larger than the source region, and we need to find out how much more counts there will be, and this is just defined by the difference in sizes of the two, and we can get this from the parameters in the header. So this is this factor that we get from this from the size difference, which we then need next, because now what we do is to define to further define the factors that come in this background model. So first we have this constant. If you remember, it was this here, which we have here. We will then fit for this value and tie this value to this. And then what we have next is in the PCA background, so in this particle component analysis, we have an additional normalization, and those we just fit set to 1 and then to -1. So this second thing is the step size. If you remember, if we set it to a negative value, it means that the parameter is frozen. And this here we just set to 1 over this background factor and freeze it. And then those parameters here, so the constants, the first one we fit and the second one we link to the first one. So both of them will be fit at the same time. Both regions will be fit using the same spectral model for the background at the same time. Then we create a prior for this normalization, which will be a log uniform prior, because normalizations typically can vary over several orders of magnitude. And then we need to append it to those transformations that we had before, so this list that I mentioned. And then finally, we can define our solver. So this here is kind of the same that we had before, just the difference is now that in these transformations we have this additional normalization, which will be fit together with the source model. Right, then we fit it again, and that's it. Actually, one step further that you can go is to then also fit a physical model to your background, but you can do this with the combination of the things that I showed you. So in this case, then you define a model not by using this this table model, but instead you just use whatever model you want to use for your background. It can also be a power law, can be some emitting gas model or something like this. Right. So summing everything up, what we do with this script is that we set up BXA and XSpec in order to do Bayesian modeling of eROSITA data, which can also be used for all other X-ray instruments, so XMM, Chandra, or whatever you want to use. We can do model comparison using BXA, and also it's easy to fit the background using the PCA model, or also to then continue using other physical models. Right, and that was it from my side. I was a bit faster than expected, but then we have more time.